Hello everybody, welcome back to Mathematical Statistics. When we last left off, we were in the middle of an example for a confidence interval for a two-sample problem, and I will get back to that, but I actually want to talk about all the questions I've been getting on the grad problem, number 7 on the current homework, and also how it relates to the last example that we actually completed. And then I'll get back to the example we were in the middle of. I'll start over. So the grad problem was problem 7, and what we had was a random sample of size n1 from a normal distribution with some mean mu1 and some variance sigma 1 squared, and then we had an independent random sample of size n2 from a normal distribution with its own mean and its own variance, so mu2 sigma 2 squared. And in problem 7 on the current homework, you were asked to look at the sample variances, and you want to show that the square root of s1 squared over n1 plus s2 squared over n2 over sigma 1 squared over n1 plus sigma 2 squared over n2, you want to show that this converges in probability to 1. So let me back up to tell you why you want to show this. So I'm going to not show this moment, but we were coming up last time with a confidence interval for a difference between two means, mu1 minus mu2. And we assumed large samples. And so in the large sample case, it's okay to use x1 bar and x2 bar in place of mu1 and mu2 by the central limit theorem. And it's also okay to use the sample variances in place of the true variance. And the reason is, well, because they're good estimators, but more formally, if we're looking at the pivotal quantity, x1 bar minus x2 bar minus mu1 minus mu2 over the square root of s1 squared over n1 plus s2 squared over n2, I said, okay, it's approximately normal 0, 1. But what we really need to say is that this is x1 bar minus x2 bar minus mu1 minus mu2 over the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. In the case that we have normal distributions, this is definitely a normal 0, 1, and yet this is not equal to the thing before it. So I'm going to have to divide or multiply by the square root of, let me divide to make it look like a homework problem. I'm going to have to divide this whole thing by the square root of s1 squared over n1 plus s2 squared over n2 over sigma 1 squared over n1 plus sigma 2 squared over n2. So if you do have normality, then this is a normal 0, 1. And if we show that this goes in probability to 1, that's how we can formally say the whole thing converges in distribution to a normal 0, 1 divided by 1 using Slutsky's theorem, and that would have a normal 0, 1 distribution. So that is the formality behind saying, oh, this acts roughly like a normal 0, 1, which we didn't show. We just said, oh, it's roughly like that, so we put it between two z critical values. But what we need is to show that this converges in probability to 1, and that's what the grad problems are that's what the grad students are doing in problem 7 on the homework. So I've heard a few approaches here that I wanted to warn you against. I've seen, going back to problem 7, I've seen some people try, well, first of all, let's just get rid of that square root. Let's ignore the square root, because if we can show that this thing inside is going in probability to 1, then we can use the continuous mapping theorem to put them both in a square root, using the continuous function g of x equals the square root of x, which actually has a continuity issue when x equals 0, but we're okay because our thing under the square root here is going to be 0 with probability 0. In other words, it's going to be greater than 0 with probability 1. There's no way it's going to land on that value because things are nice and continuous. So it's enough to just show that s1 squared over n1 plus s2 squared over n2 over sigma 1 squared over n1 plus sigma 2 squared over n2. We want to show that this goes in probability to 1. There are a few ways you can go about this. I would take advantage of the fact that the distributions were normal here, rather than having to try to make like a variance goes to 0 argument. I don't know if you remember when we looked at the variance for the sample variance, it was an ugly expression involving the fourth central moment of the distribution, but we don't have to worry about that here because we do have normality in this example in problem 7. So I would probably use, and so here's another thing that I've been seeing people do incorrectly or trying to do incorrectly. You don't want to show that s1 squared over n1 plus s2 squared over n2 goes in probability to sigma 1 squared over n1 plus sigma 2 squared over n2. That just doesn't make sense at all, because this is a convergence as the sample size, in this case sample sizes, plural, gets large. So you can't have these n's on the right-hand side because they're going off to infinity in that arrow. So you definitely can't do this, so I would stick with this. In terms of the limits that you will have to take, it's enough to take the limit in both directions. So take the limit with respect to, say, n1 first, and then with respect to n2, and show that goes to 1, and then switch the order. So with respect to n2 first, and then with respect to n1 second, and if that still also goes to 1, then the limit is going to go to 1. You're not going to have any issues like it blows up in one direction and not the other. And as far as your homework problem goes, I don't really care if you look at both of those. So just pick an order, even though technically that's not quite enough. So to finish this off, let me give you a big hint on how to show this is converging in probability. I would use that theorem we had that said that if you have theta n hat as an unbiased estimator of theta, and the variance of theta n hat goes to 0 as n goes to infinity, in this case as n1 and n2 go to infinity, then your theta n hat is converging in probability to theta. So the theta here is going to be this 1 if you, number 1, take the expected value of this whole expression. I know you're thinking cut and paste would be faster, but trust me, I bungle that pretty often. So you can show that this is equal to 1. And then if you show the variance of this goes to 0, as you take the limit in n1 first, say, and then n2, or the other way around, technically you should do it in both, but I don't care. Then you can say this is an unbiased estimator for this, and the variance is going to 0. Therefore, this converges in probability to this. So how you would do this expectation is this denominator does not involve anything random, so you can pull the entire 1 over that whole thing in the green box out and run the expectation across, and it's not bad at all. But I want to get you started on the variance, which is the harder one, and this should also give you a sense of what to do with the expectation. If we look at the variance of s1 squared over n1 plus s2 squared over n2 over blah, 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 I am going to pull this out, and it comes out squared. So there's nothing random there, so I get 1 over sigma 1 squared over n1 plus sigma 2 squared over n2 squared times the variance for s1 squared over n1 plus s2 squared over n2. Because these variances are sample variances that came from independent samples, This and this are independent, which means you can run the variance through by independence. I'm purposely being a little bit sloppy and not writing that out here because I don't want to finish your homework problem for you, but the next step would be to run the variance across and say, I can do this by independence of the two samples. Then you might pull out the 1 over n1 and the 1 over n2 from the individual variances, and they will come out squared. So it really comes down to, can you find the variance for, say, s1 squared, and the s2 squared is going to be similar. The easiest thing, in my opinion, to do here is not to go looking at the expectation that defines this, but to use the fact that we know, given we started with normal samples, that n1, we know that n1 minus 1, s1 squared over sigma 1 squared has a chi-squared distribution with n1 minus 1 degrees of freedom. And the mean for a chi-squared is equal to its degrees of freedom. The variance for a chi-squared is equal to 2 times its degrees of freedom. That's not exactly what I have here, but if we rewrite it, this could be the variance of n1 minus 1 s1 squared over sigma 1 squared times sigma 1 squared over n1 minus 1. Then you can pull this constant out, which will come out squared, and you're left with the variance of a chi-squared n1 minus 1, and that variance is 2 times that degrees of freedom. If you don't remember the chi-squared variance, I realize it's not in your table. Look at the gamma, because this is in our parameterization. This is a gamma n1 minus 1 over 2 comma 1 half, and you can look that expectation and variance up in the table. So it's a lot of algebra. Yeah, it's a little bit tedious, which is why I don't care if you show the limit with n1 first and then n2 and then the other way around. I'm just telling you it comes out to be the same, so everything's good, and I'd be happy if you just take one of those limits. Okay, so let me know if that doesn't make sense. Otherwise, let's go back to the example we were working on. We weren't that far into the example, so I'm going to start it all over. What we had is a random sample of size n1 from a normal distribution with mean mu1 and variance sigma 1 squared, and then we had an independent random sample of size n2 from a normal mu2 sigma 2 squared. We want to derive a 100 times 1 minus alpha % confidence interval for the difference in means mu1 minus mu2, and we don't know, in this example, we don't know sigma 1 squared and sigma 2 squared. We also don't know mu1 and mu2, or we wouldn't be doing this. And we can't assume large samples. So if at least one sample, like n1 sample size, is small, or n2 less than or equal to 30, then we are going to have a problem plugging in s1 squared for sigma 1 squared and s2 squared for sigma 2 squared, because we did that based on a convergence improbability result, and that assumes things are getting large, the sample sizes are getting large. But if we can't assume large samples, then this is not going to be a good approximation of this, and the same for the second variance. So if we had small samples, or at least don't know that we have a large sample, in the case where we had a single mean and we came up with a confidence interval for mu, a single sample, this is where the t distribution came in, and it's going to come in here as well. So we're going to break this into two cases. Case 1 is where we can assume that sigma 1 squared is equal to sigma 2 squared. I don't know how you feel about this, but if we don't know the means, we said we don't know the variances, why would we know they're equal? I've got 3 replies for you. Different ones. So 1, we can say this would never happen, that we would know this, but it's a building block example. So let's just assume that sigma 1 squared is equal to sigma 2 squared. Number 2, we could make some argument about the actual problem of interest. I gave an example, a stupid example last time about us selling cereal in a grocery store and having a special like limited edition box, and us having some kind of historical data where we saw that putting these special boxes out, we increase sales, but historically we have convinced ourselves that it doesn't change the variance. So maybe sample 1 comes from before we replace the box, and sample 2 comes from after we replace the box. And so if we're making a confidence interval for mu1 minus mu2, maybe we want to show that this confidence interval includes negative numbers, which would suggest that this is larger than this, and that we're actually making more money with the new boxes. But we have this historical data to say that we believe this is true. The third thing you can do is a hypothesis test, which is coming up next. It's actually coming up today, to say, looking at your 2 sample variances, S1 squared and S2 squared, we can perform a test for whether or not we believe this is true, if the data is lending evidence towards this. So we could either just assume it's just given, it's a building block, or we believe it's true from historical data, or maybe we went ahead and did some kind of test for this before we did this confidence interval. So I'm assuming they're equal for case 1. And let's continue. So if they're equal, there's just 1 sigma squared. I'm going to call the common value sigma squared. So sigma squared is equal to sigma 1 squared is equal to sigma 2 squared. And I have these 2 samples, one of size n1 and one of size n2 from different populations with different means. And so we're going to use sample variances, S1 squared and S2 squared. And these are both trying to approximate the same sigma squared, because this is an approximation for sigma 1 squared, and this is an approximation for sigma 2 squared, but we're assuming they're equal, and we're just calling the common value sigma squared. But we end up with 2 sample variances from the different sample. You might think of throwing all the data together, making a big sample of size n1 plus n2, but the sample variances are, average squared deviations away from the sample mean, and the sample means are likely different here. I mean, that's what we're trying to figure out, because we're not assuming that these means are the same. So I wouldn't just throw them into one big sample to compute a variance with n1 plus n2 data points. Instead, we talked last time about a couple of possibilities that maybe were not good ideas. One was to estimate the common value, so estimate sigma squared with the average, which is 2 squared over 2, to bring those pieces of information together. There's a couple of problems with this. One is that it's just not easy to work with as we go forward in our confidence interval and have to find the critical values and stuff like that. But a big other reason would be if the sample sizes n1 and n2 are very different, then you would expect if the first sample size is much larger than the second. If they're both large, we don't have to worry about any of this, but at least one of them is small. And if the first sample size is much larger than the second, then the first sample variance is probably a much better estimator for sigma squared than the second sample variance, in which case we would like to give this one more weight. So this is not a good idea. A second idea would be to try to use some sort of weighted average, which will give the sample variance from the sample from the larger sample, will give it more weight. So something like n1 s1 squared plus n2 s2 squared over n1 plus n2. This is a much better idea for that reason that if n1 is like large, then this sample variance is a much better estimator for the thing we want, and we should give it more weight in our estimator for sigma squared. And so if this was large, oops, sorry about that. If this is large and this is relatively small, then this expression here is going to give more weight to s1 squared. That's a good idea in terms of weighting them, but again, it's not something we can easily work with in our 4 steps for a confidence interval. We're going to go to the next step and say, what is the distribution of this thing? And we won't know it. So the third approach is going to be the one we're going to take. So no. Instead, we're going to estimate the common sigma squared with something known as a pooled variance. And we're going to call it SP squared for pooled variance. And it's going to be almost like this, but we're weighting it just a little bit differently. We're going to use n1 minus 1 s1 squared plus n2 minus 1 s2 squared over n1 plus n2 minus 2, which is the sum of those two coefficients in the numerator. Why are we doing this? Because check this out. If you look at n1, so let me say then, if you look at n1 plus n2 minus 2 times the pooled variance over the true variance, we only have one variance here, then that's going to be this multiplied to the other side and everything divided by sigma squared. So that's going to be equal to n1 minus 1 s1 squared over sigma squared plus n2 minus 1 s2 squared over sigma squared. And we already know, starting with the normal distributions for our random samples here, that this first term has a chi-squared distribution with n1 minus 1 degrees of freedom, and this one is a chi-squared with n2 minus 1. And these two terms are independent because they're computed from these sample variances, which come from independent samples. And we know that if you add independent chi-squareds, you get another chi-squared. And the degrees of freedom comes from adding the original degrees of freedom. So we know that this whole thing is chi-squared. And then if I add this and this, I get n1 plus n2 minus 2. So something nice that we know the distribution of. Okay, so x1 bar, we do know, is normal with mean mu1 and variance sigma 1 squared over n1. And x2 bar is normal with mean mu2 and variance sigma 2 squared over n2. And I guess there's not sigma 1 squared and sigma 2 squared anymore, so let me remove those subscripts there. This means that x1 bar minus x2 bar has a normal distribution with mean mu1 minus mu2 and variance sigma 1 squared over n1 plus sigma 2 squared over n2, and we get that using the independence of the samples. That allows us to combine the variances like that. And this means that x1 bar minus x2 bar minus mu1 minus mu2 over the square root of, I keep putting the sigma 1 and sigma 2 in there. I guess it's okay because I wrote above that they're both equal to sigma squared, but yeah, let me take that out. I'm going to write this as a single sigma squared 1 over n1 plus 1 over n2. And that's what I'm going to put under the square root here. So we do know that this is normal 0, 1, because we took something that is truly normal, nothing large sample about it. We subtracted the mean and divided by the square root of the variance, and that's a standard normal. But this can't be our pivotal quantity that we put between two critical values to make a confidence interval, because then if we solve down for mu1 minus mu2 in the middle, the endpoints of our confidence interval will involve the unknown sigma squared. So we're going to replace it with our pooled variance. If we start with x1 bar minus x2 bar minus mu1 minus mu2 over the square, I'm writing bigger and bigger, and I need a lot of space, so kind of regretting it, but if we replace it with the pooled variance, the question is, what is the distribution here? This is equal to x1 bar minus x2 bar minus mu1 minus mu2 over the square root of sigma squared 1 over n1 plus 1 over n2 times the square root of sigma squared over the pooled variance. This is x1 bar minus x2 bar minus mu1 minus mu2 over the square root of sigma squared 1 over n1 plus 1 over n2 divided by the square root, I'm going to leave some space here, the square root of sp squared over sigma squared. You see something forming here. This is normal, 0, 1, and this is something that's almost a chi-squared under a square root. This is starting to look like a t-distribution, but the thing that in the bottom is not a chi-squared, and also to get the t-distribution, you need to divide by the degrees of freedom. Let me extend this square root down a little bit. If I go in and multiply by n1 plus n2 minus 2, and also divide by that, then this thing in here is chi-squared n1 plus n2 minus 2. This thing up here, again, is normal 0, 1. The two circled things are independent for the same, we haven't shown this, but we did show it using that long Jacobian problem when we had one sample. We showed that the single sample variance is independent of the single sample mean. And so you can argue that S1 squared is independent of this and also independent of this because it's an independent sample calculation. And so you could argue the same sort of thing. But my point is that this entire thing has a t-distribution with n1 plus n2 minus 2 degrees of freedom. That's a lot of lines. So let's pull it all together and go back to the confidence interval. Step 1, and this is a confidence interval for mu1 minus mu2. Step 1 is to choose a statistic, or you might say an estimator. And we did x1 bar minus x2 bar. Step 2 is to find a pivotal quantity, which is a function of this x1 bar minus x2 bar and the mu1 minus mu2, whose distribution is known to us and unknown parameter free. That is, it's not depending on any unknown parameters. And I won't write that step out in here. We just did all that work. We're going to use x1 bar minus x2 bar minus mu1 minus mu2 over the square root of sp squared, the pooled variance, 1 over n1 plus 1 over n2. And note that this has a t-distribution with n1 plus n2 minus 2 degrees of freedom. So step 3 is going to be to find critical values, and we're going to use the t-distribution. Still writing bigger and bigger. Let's call this t. I know that I can get area 1 minus alpha as a probability that t is between a couple of things. I'm going to look at the t curve with n1 plus n2 minus 2. This is the PDF. And this is a symmetric curve centered at 0, so it makes the most sense for us to capture this area right in the middle in order to get the shortest confidence interval. You do not have to give me the shortest confidence interval in this class. It's not always going to be obvious, and so don't worry about it. But I think given what we talked about, it's pretty clear here, because if you try to go like from here out, it's not going to be the same width because there's so little area out here. You're going to have to go out further to capture it. Okay, so we have names for these critical values. This one is t sub alpha over 2 because we have alpha over 2 up here and alpha over 2 here. And then something that shows the degrees of freedom. And then this one is t, well, it's the negative because we're nice and symmetric. If it wasn't symmetric, I would call this t sub 1 minus alpha over 2. But those are the two things that go here and here. And I'm just too lazy to write that. So write these critical values in here. Put this in the middle. And then solve down the system of inequalities to capture or to isolate mu1 minus mu2 in the middle. And we get the answer. So step 4 is our kind of conclusion here. A 100 times 1 minus alpha percent confidence interval for mu1 minus mu2, and my usual laziness, when we have a sample of size n1 from a normal mu1 and sigma 1 squared, and an independent sample of size n2 from a normal mu2 sigma 2 squared, and we don't know the variances in addition to not knowing the means, and we have at least one small sample. You're going to end up with x1 bar minus x2 bar plus or minus t sub alpha over 2, comma, n1 plus n2 minus 2 times the square root of sp squared, 1 over n1 plus 1 over n2. And for what we did, we don't need any small samples. This is really what you should do when you have the normal distribution and you're using sample variances in place of true variances. But as I said before, if you go to a t-table to try to actually find these critical values, you'll see that the t-table gives you these values for like 1 degree of freedom, 2 degrees of freedom, maybe up to 30 degrees of freedom. And after that, it's just so close to the z-table anyway that people often don't think about the t-distribution. So again, what I'm trying to say is normality, sample variances instead of true variances should be a t-distribution, but usually people only do that if you have a small sample. So that is case 1 for this problem, where we assumed the true variances were equal. And if we can't, it's actually a much harder problem that does not have an exact answer. So case 2, we can't assume sigma 1 squared equals sigma 2 squared. There is no exact answer here. This problem is known as the Behrens-Fisher problem. And the most common solution to this problem is that Behrens and Fisher, Welch's approximation. So Welch showed that, this is called Welch's approximation, showed that x1 bar minus x2 bar minus mu1 minus mu2 over the square root of s1 squared over n1 plus s2 squared over n2 is approximately, and there is a formal statement to be made here, but it's not a convergence and distribution result. It's just not exactly known, even for large samples. But approximately a t-distribution with n degrees of freedom, where n is s1 squared over n1 plus s2 squared over n2, all squared over s1 squared over n1 squared over n1 minus 1 plus s2 squared over n2, all squared over n2 minus 1. And then n should be an integer, and this is not going to be an integer. So you want to round it, and you want to round it down to the nearest integer. Why? Because we've got a lot of uncertainty here. And the t-distribution, the lower the degrees of freedom, the wider it gets, the more smushed that bell curve gets. And then numbers cutting off, say, 95% area in the middle, as you squish it down, they're going to stretch out. And so you should be conservative here and go for that longer confidence interval rather than rounding this up and getting something just a little bit narrower. So again, this is known as the Behrens-Fisher problem, and by far the most common way to approach this is using Welch's approximation. I'm not going to test you on this, I just wanted this for your information. If you're using software like R, we're not using any software in this class because it's really theoretical, but if you use R to do a hypothesis test or create a confidence interval, you are going to see Welch's approximation being printed out as part of your answer a lot of the times. And that's because R is doing something like this behind the scenes. Okay, so this concludes our discussion on confidence intervals. It's not the last confidence interval we're going to make, but we've got the idea, and we've seen a couple of examples so far that do not involve normal distributions. As long as you know your steps, step 1, step 2, step 3, step 4, then you can pull this off, assuming you can choose a statistic for which you can find a pivotal quantity. On the current homework and any exams coming up, I will give you the statistic to start with. We are getting close to having methods of coming up with good statistics and estimators for unknown parameters, because so far it's just been the common sense thing or things we can work with, but we're going to have formal algorithms for estimating parameters. And I'm going to put it off just a little more. I really want to get to it. I sense that you do too. But I want to spend some time doing a normal introduction to hypothesis testing. And here's why. At the end of this class, we're going to be doing really general hypothesis testing. It's going to be really abstract and weird, and you're going to feel so powerful, the things you can test, because we're going to be removing a lot of simplifying assumptions. But hypothesis testing has its own language. And one of the biggest stumbling blocks, I think, that I see in students is just getting lost in the terminology. So I like to do an introduction to hypothesis testing, just working with normal distributions for now, or maybe we can do another example that's not normal, but a basic and kind of simplistic introduction. Then we're going to go into estimation, which is going to be a big part of this course. Things like maximum likelihood estimators, if you've ever heard of those. The UMVU, which stands for Uniformly Minimum Variance Unbiased Estimator, which means if every one of you has an unbiased estimator and I have an unbiased estimator, I can guarantee you that I did better than yours, or we have the same estimator. It is uniformly the best unbiased estimator in terms of small variance in the entire universe. And that, yes, is as cool as it sounds. So after we do all this cool estimation stuff, we're going to get back to hypothesis testing sort of more seriously. But having seen it now will give you a chance to let it sink in a little bit so that when we do that, you don't have to do all that harder abstract stuff in addition to just like the basic terminology. I took way too long to say that. So I call this a mostly normal introduction to hypothesis testing. Let's start with a motivating example. Suppose we have x1, x2, etc. through xn, IID normal with some mean mu and some variance sigma squared. And I'm assuming that mu is unknown, but assuming that the variance is known because it's a building block example. Suppose that I don't really want to estimate the true mu as much as I want to determine whether it's in one region versus another. So suppose we need to know whether mu is like less than or equal to 2.8 or mu is greater than 2.8. One way to do this would be to estimate mu with a sample mean, but that will not allow us to draw a conclusion. First of all, we're going to have to look at the variance, because if the true mean is in this region, so let's say it is 2.5, then x bar has 2.5 as its mean. And the value that you see for x bar, I mean, it's sampled from this distribution. So it could be here, it could be here, it could be here. You know, it's mostly towards the center. But you can easily get, well, I don't know, I don't have a sense of scale on here, but you could easily get like, I don't know, 3.5, even though the mean is truly less than 2.8. So if you just estimate x bar, you would also have to look at the variance and try to make a decision. And hypothesis testing formalizes that decision for us. So we're going to see whether or not the data supports this hypothesis or this hypothesis. Again, it's just going to be a little more formal than saying, oh, well, we saw a sample mean that's in this range, but we know the variance is very large, so that doesn't mean we're not in here. And so, again, a series of steps, four steps again, or 3, depending on how you want to count them. I'm not ready to do one of these tests. We're getting some terminology and notation, but step 1 is going to be to choose a statistic on which to base the test. So let me stick with these 2 hypotheses. Is mu less than or equal to 2.8, or is mu greater than 2.8? And I have notation coming up. I think some of you have seen this, the little HO and the HA or the H1. So look at a statistic, probably x bar here, because that's our most common sense estimator for mu. But part of the advanced hypothesis testing at the end of this course is going to show you exactly what statistic you should look at to get the best result. And we're also going to define what it means to have a best or better test than someone else. And so I think we're going to do something like go with the conclusion that mu is greater than 2.8 if x bar is large in some sense, and we need to figure out exactly how large is large, i.e., if x bar is greater than a constant c, where c is given, so that we give someone with data the recipe to draw the conclusion. All right, let's set up some hypotheses. Sorry if this is too basic. I know there's a lot of people in here who haven't had any stats before this. So we have what is called a null hypothesis. This is going to be written as H0, and then we put a colon, and then we put the thing, well, we put one of these things. So the one we put here, let me finish this. Then we have an alternative hypothesis. A lot of people use H sub A for alternative, and a lot of people use H sub 1. I'm a little partial to H sub 1 in a math stat environment. But if you use HA, that's fine. So mu greater than 2.8. The null hypothesis in hypothesis testing is always assumed to be true. And then if you look at your data and look at X bar and you find strong evidence that this seems to be true based on the data, all right, alternative, then you will reject the null hypothesis in favor of the alternative based on the data. So the alternative hypothesis is what you are out to show. This depends on your point of view. Suppose we still have that cereal company and we have, I don't know how many ounces in a normal box of cereal. I'm just going to make something up. Let's say our cereal boxes are supposed to contain 32 ounces of cereal. No idea if that's even a good number. And suppose an angry consumer group is like out in our parking lot marching with signs and they think we're underfilling the boxes. So we might want to show that that's not true, and they might want to show that it's true. So us, in this cereal example, and I'm sorry, I don't have the setup written down, so this might not make a lot of sense, but we are going to assume that the actual average in our cereal box is less than or equal to 32 ounces, and we're going to be out to prove to those people that the actual average is greater than 32 ounces. That's what we're out to prove. But for the angry mob, they're going to assume that we're doing okay with our cereal boxes, but they would like to prove so they can come to us in court that the true mean is actually less. So null hypothesis is assumed to be true. The alternative is what you're out to show, and what you're out to show depends on your point of view in a particular problem. Right. As we get going into more generic hypothesis testing, we're going to be looking at a parameter, theta, which will live on a parameter space. If theta is the lambda for an exponential distribution, it lives on the interval from 0 to infinity. If it is the p for a Bernoulli distribution, it lives between 0 and 1. If it is the mu for a normal distribution, it lives everywhere from minus infinity to infinity. So there's always a parameter space, and I'm eventually, you don't need to know this until we get towards the end of the semester, but I'm going to use this kind of capital theta to denote that space. And then we're going to let this capital theta naught be some kind of subset of the parameter space. And it could be a very weird subset. It doesn't have to be an interval or anything involving a less than. And our null hypothesis is going to be that theta is in this subset versus the alternative that theta is in the rest of the space. So the subset complement, or the complement is taken with respect to this space. And this is going to be potentially very strange. It's going to be really cool when we get to general hypothesis testing, away from means, away from normality, away from simple inequalities. But right now, that is what we're doing. I'm going to scroll back to my example here. So if the true mean, mu, is 2.5, and if we call this the null hypothesis and this the alternative, then if the true mean, and we'll never know this, is 2.5, then the null hypothesis is true. But especially if there's a large variance, X bar can actually go all the way up to infinity, right? X bar can definitely look like it's in this range, even though this is true. So we're going to find a cutoff, and we're going to say, if X bar gets above this number, that's enough. I am going to say that this is no longer the right distribution. But if it's below the number, I'm going to go with this. And so we're going to find a cutoff. We're going to call it C, and we may be wrong. We're not going to know for sure, we're going to be looking at a single sample and the X bar in that sample, and we might get an outlier sample that has a very large sample mean when really the mean is smaller, or vice versa. So there's going to be mistakes, and it's not because you did anything wrong. It comes from the probability of getting these freak samples and us not really knowing exactly how large this should be before changing our mind that this is true versus this is true. Again, I don't know if I said this, but we are not proving anything. And we never are showing that this is true. We're always assuming the null hypothesis is true. And then if the data strongly suggests this, we didn't prove that that's true, but we're going to go with that hypothesis. We're going to say, we believe that this is true based on the data we saw. It supports this conclusion. So no proof here, and definitely no showing the null hypothesis is true. That's assumed to be true. Okay, so we're going to find a cutoff C. Maybe in this picture, C is 3.8. I'm going to say if the sample mean X bar is greater than 3.8, then I no longer believe that this is true, and I'm going with this one. We might make a mistake, and so let's talk about errors in hypothesis testing. A little nonlinear today. I keep saying, you know what, I have to do this first. There's something I have to do first before talking about errors, and that is the idea of a simple versus composite hypotheses. Hypothesis. A simple hypothesis is one that completely determines the distribution. For example, if we have a normal distribution with an unknown mean and say variance 1, the null hypothesis that mu is equal to 2.8 is a simple hypothesis, because if that hypothesis is true, we know exactly the distribution. We know we're working with a normal 2.8, 1. The same is true if I have a normal mu sigma squared, where sigma squared is known. Because then we're working with a normal 2.8, sigma squared, and sigma squared is known to us, so we know the exact distribution, and that makes this a simple hypothesis. In a Stat 101 course, it's a common mistake to say that hypotheses with an equal sign are simple versus hypotheses with an inequality not being simple. Let me say a little bit more about that. So keeping with this example, a null hypothesis like mu is less than or equal to 2.8 is a composite hypothesis, which is the opposite of simple. If the null hypothesis is true, the data comes from a normal what? A normal 2.81? A normal 2.751? I mean, there's an infinite number of possibilities here, and I don't know exactly what distribution we're working with. So this is not simple. It is instead composite. I was just saying that a lot of people say, well, if you have an equal sign, it's simple, and an inequality, it's composite. That's not exactly true, because as another example, if we have a normal distribution with mean, mu, and variance sigma squared, and they are both parameters are unknown, a null hypothesis like mu equals 2.8 might look like a simple hypothesis because it has an equal sign, and if it's true, I know that the mean is 2.8. The problem is that sigma squared is now unknown. So if this null hypothesis is true, then the data come from a normal 2.8 sigma squared distribution, but the problem is we don't know this. So the distribution is not completely known to us. That means that in this example, this is a not simple, therefore a composite null hypothesis. So simple hypothesis completely determines the distribution. If you know that hypothesis is true, then you know exactly what distribution you're working with. Otherwise, it's a composite hypothesis. And we can talk about the null hypothesis being simple or composite, and the alternative being simple or composite. I said we were going to talk about the types of error in hypothesis testing. We're going to start by defining them in a simple case. Let me get a subject header here. Simple versus simple hypotheses. Suppose we're testing whether a mean mu is equal to some value versus the mean is equal to some other value. This could be like a 3 and a 5, but more generally, I'm going to say mu equals mu naught versus mu equals mu 1. And the mu naught and mu 1 are known to you. If you're doing a hypothesis test like this, then these are your two possibilities. So you're going to assume that this is true, and if your sample mean is negative 47 billion, this is probably not true, so you have to go with this one. That doesn't look true either. But again, you're assuming this is true, and if there's evidence for this, then you're going to go with the alternative hypothesis. And in hypothesis testing, you assume that the two hypotheses make up the entire set of possibilities. So we're kind of restricting the parameter space. Instead of saying that mu can be anywhere from minus infinity to infinity, we're doing a simplistic problem that says that mu can only take on one of two values, number 3 and number 5. This is overly simplistic, and it is a starting point building block for us. So in the case of simple versus simple hypotheses, we've got two types of error. Again, I just want to emphasize this is for simple versus simple. And I'm going to describe these in like a 2x2 table. Over here, we'll talk about reality. And the reality is either that the null hypothesis is true or the null hypothesis is false. And then up here, I'm going to put your decision. So either you, and this is in quotes, I have to say something about this, you accept the null hypothesis or you reject the null hypothesis. Remember what I said about we can never really prove what's going on here. We just get evidence for something or against something. And I also said that the null hypothesis is always assumed to be true. Our conclusions are either going to be, looking at my data, I reject the null hypothesis or I fail to reject it. You never want to use language like accept in hypothesis testing. I'm doing it one time to get a nice clean binary table here, but I'm not going to use it after this table. So your decision is going to be to reject the null hypothesis or fail to reject it. It's like an innocent, no one's proven innocent in an American court. That they're guilty or they're not guilty. It's just like that. So I'll do it for this table though. If the null hypothesis is true and you accept it, you did good. If it's false and you reject it, you did good. Otherwise, you made a mistake. And the first mistake in this upper right box is known as a type 1 error. So that's what you get when the null hypothesis is true and you reject it. So you made the mistake. And the other one, guess what, is called a type 2 error. A little squished. Alpha, we're going to use to denote the probability of making a type 1 error. And beta is usually used to denote the probability of making a type 2 error. Alpha and beta do not have a 1- relationship. They will in some examples, but they're not necessarily going to have that. It will just happen that will be the case. And the reason is because when the null hypothesis is true versus it's false, these are completely different universes, and you're in one of them. So if we're in the universe where the null hypothesis is true, we're going to reject the null hypothesis with some probability alpha. That's the probability of making that type 1 error. And therefore, we're going to quote-unquote accept it with probability 1 minus alpha. So this is getting entirely too messy. But just if I was matching that picture, this is like probability alpha and 1 minus alpha. And then the beta stuff lives in a different universe. So beta is not 1 minus alpha, although we will see that happen in some cases. Okay, I am out of time. So in the next example, we're going to actually start finding hypothesis tests. So here's where it gets good, and here's where, unfortunately, I am out of time. These errors are going to be given to you by the person invested in the problem. Someone will come to you as a statistician and say, can you do a hypothesis test for me? And this is the amount of error I'm willing to accept. So someone's going to give you an alpha and maybe a beta as well. And then we're going to use that to find the cutoff value, the C, if you will. We had a rule that looked like this, and we're going to find the cutoff that will make sure that the test will have the alpha and possibly the beta that that person wants. But I'm out of time just when it got good. So I'm sorry, I rambled on and on. We didn't get very far today, but hopefully I served my purpose of getting us into the language of hypothesis testing. Please come back next time on Mathematical Statistics.